is their shared secret. Okay. So now the problem is, see, in the normal logarithm, when normal or the continuous logarithm is finding the power. Okay. So if a raised to x is m, then log of m to the base a is x. We find the power to which, when the base is raised, we will get m. So what power of a is m? That is the continuous log or the normal log that we know. The discrete log, discrete log is when we had used the alphabet h yesterday. So as I had said, the attacker knows the prime number p, the modulus is known, and basically the attacker can see either of these values. Okay, attacker cannot see this because it is the shared secret, but they don't transmit it again amongst themselves. It remains on their side. G raised to BA mod P remains with A, and G raised to AB mod P remains with P. It is not transmitted, so there is no chance of leaking this value. What is leaked? Either G raised to A mod P, G raised to B mod P. Okay, so let let H be equal to G raised to X mod P, G raised to X mod P, and the discrete log of H to the base G is equal to X. Okay, modulo is assumed. I'm not writing in this notation, but with this mod, we have to calculate the value of X such that G raised to X mod P is H. So the attacker knows the value of H. Okay, we are thinking from the attacker point of view, like how can the attacker crack this system? So there is an underlying uh, belief or principle behind this Diffie-Hellman key exchange, that this problem is difficult to solve. This problem is difficult to solve because of the added modulus, especially. Okay, because yesterday we had seen an example. Let's say if we want to calculate 2 raised to x is 140, then we can find uh, between two powers of 2. So between 7 and 8, as we had seen yesterday. Then between 7 and 7.5 we can see, and so on, we can find that value. But now, since there is mod p, so it can be any power as such. So it becomes a difficult problem because of the added modulus. This is the discrete log problem. Given a prime number p, a primitive root g, which you can calculate. It may not be given, but you can calculate the primitive root g. Okay, find the x such that g raised to x mod p is equal to h. Or other way of writing this is g raised to x is congruent to h mod p. Okay, so one method is the brute force method, trial and error. You'll start from x equal to 1, you know, brute force. You'll try all the possible values of x, and you'll actually find the value for which you get h as the answer. So that value of x will be your answer. First one is the brute force, which you are not interested in. Okay, we are not interested in trial and error. or brute force in this case. Then, okay, now this method is called as baby step, giant step method. Baby step, giant step method. Okay, so the algorithm is as follows. Okay, so first we calculate capital N as the square root of p minus, sorry, not okay. So we'll calculate the square root of p minus 1, and then we take the ceiling. This is the ceiling. Okay. So ceiling, do you understand? Ceiling of a number. Can anyone tell me? - 5.5 is 6. Upper round value. Okay, so yeah, so it can be anything, right? So ceiling value of let's say 3.1. Ceiling value of 3.1 is 4. And similarly, there is another function which we are not interested in right now here, but it is called as the floor function. And floor of 3.1 is 3. Okay, so you get the concept basically. 3 point something means you have entered the territory of 4 for the ceiling. Ceiling is 4 and floor is 3. Okay. So you calculate the ceiling of square root of p minus 1, the first step. Then you will make two lists. You will make two lists. First is g raised to I, g raised to I mod p, where I goes from 0 to n minus 1. This is the first list. And the second list is h times g raised to minus n multiplied by j mod p, where again j goes from 0 to n minus 1. Okay, so at some point, for some value, these two lists will match. These two lists will match for some value. So find a match between the two lists. So let's say they match at g raised to I mod p in the first list. Okay, and h into g raised to minus nj mod p in the second list. So note the I, j for which this happens. Note the I and j for which this happens. Then your answer is x is equal to I plus nj. This is your answer. Note the I and j and calculate x is equal to I plus nj. That will be your answer. So this is the baby step, giant step method. One of the list takes baby steps and another list takes giant steps because it is multiplied by minus n, therefore these are giant steps in a way. Baby steps, giant steps. Okay. So let's take an example. We want to solve 2 raised to x is congruent to 9 mod 19. We want to find the power of 2 such that 2 raised to x mod 19 is 9, or okay, 2 raised to x is congruent to 9 mod 19. So the first step is n is equal to ceiling of square root of 19 minus 1. 19 minus 1 is 18. So 9 into 2. So it is 3 multiplied by square root of 2. Okay. 3 multiplied by square root of 2. Square root of 2 is 1.414 approximately. So 4.2 and the ceiling will be 5. Verify this. Ceiling is 5. Right. Then, okay. Then second step, make two lists. So so the list will go from 0 to 4. 0 to n minus 1, that is 0 to 4. So the first list is 2 raised to 0 is, and you'll calculate modulo 19. So 2 raised to 0 is 1, 2 raised to 1 is congruent to 2, 2 raised to 2 is congruent to 4, 2 raised to 3 is congruent to 8, 2 raised to 4, okay, 2 raised to 4 is congruent to 16 as it is. Now the second list, 9 times, okay, so I'll just write the values for your reference. Here g is 2. Now how did you know that g is 2? Because maybe you will have to find, but let's say we know that 2 is the uh, primitive root for 19 in this case. Okay. Actually, maybe you'll first have to verify whether that is, or it will be given in the question that it is a primitive root. You just go ahead and use the algorithm to find the answer. Okay. So and h is 9. We want to find x. So according to the second step, 9 times, that is h is 9. So 9 times 2 raised to minus n times j. J also goes from 0 to 4. Okay, so 2 raised to minus, now n is 5 common multiplied by 0. Okay, which is congruent to 9. And second one will be 9 times, I'll use multiplication. 9 times 2 raised to minus 5 into 1. Okay. Now how will you calculate this? You have to calculate the value of this mod 19. Yes? No. So to be, okay. This step is you have to calculate h times g raised to minus nj mod p. That is where I have stopped. That is where I have stopped. And I want to discuss this. We can calculate that by 9 upon 2 raised to 5, that is 9 upon 32 mod 19. Don't go into the decimals, okay? Think of this as 9 times 2 raised to minus 1 times 2 raised to 5 mod 19. 9 mod 19 divided by 32 mod 19. Okay, think of it this way. This is actually 9 into 2 raised to minus 1 into, no, sorry. Okay, 2 raised to minus 1 raised to 5. I meant this. 2 raised to minus 1 raised to 5 mod 19. Okay, that is 9 times 2 raised to minus 1 times 2 raised to minus 1 times. Okay, this entire thing. Okay, okay. Do you agree with this step? Yes. Okay. So now 9 mod 19. So we'll have to find the individual values. So 9 mod 19 is 9 itself. 2 raised to minus 1 mod 19. We have to find the multiplicative inverse of 2. Right? How will you find? Okay, so let me ask you. I want to find this quantity. Have we seen this before? Have we calculated something like this before? By finding GCD and then the value of x, right? You're on the right track. So basically 2x is congruent to 1 modulo 19. And then we used to solve with the extended Euclidean algorithm to find the multiplicative inverse. Okay, we are finding the multiplicative inverse of 2 modulo 19. So because this is just 2, and can you just find the value like without going through the algorithm in this case? Okay, one way is we can use the extended Euclidean algorithm and then we can find the value of x. 10. Yes, 10 is correct. 10 is correct. So x is 10. So now we have 9 into 10 raised to 5. 9 into 10 raised to 5 mod 19. Okay. Okay. Is there any, how can you calculate this? Okay. 90 into 100 into 100 mod 19 is one way to break this. Then if you calculate separately, 19 fours are 76. So here it will be 14. Here it will be 5. Here it will be 5. Mod 19. Okay. Then 14 into 25 mod 19. So 14 remains, 25 comes 6. So 14 into 6 mod 19. 14 6 are 84. 84 mod 19, which is 8. This entire thing was the calculation for 9 into 2 raised to minus 5 mod 19. Yes, some of you have got 8. Good. Okay, I'll repeat it once because many of the parts I did mentally. So I'll just, so initially we had 9 into 2 raised to minus 5 mod 19. This we broke down as 9 into 2 raised to minus 1 raised to 5 mod 19, which is this. So what is now, as we have studied the properties of modulus, when we have a into b mod c, that is equivalent to a mod c into b mod c. That is why we will calculate the value mod 19 for each of these individually, maybe, and then we can get the final answer. No, we got the final answer as 8, not the common value. Okay, I'll just go through it once and okay, let's see. So 2 raised to minus 1 mod 19, if I want to calculate, let's say x is congruent to 2 raised to 1 mod 19. So this is same as finding the multiplicative inverse of 2 mod 19. Okay, so multiplying by 2 on both the sides, it is 2 raised to x is congruent to, sorry, 2x is congruent to 2 raised to minus 1 into 2 becomes 1. Okay, I multiplied by 2 on both sides of this equation. That became 2x is congruent to 1 mod 19. We are finding the multiplicative inverse of 2 mod 19. X is 10. Now this we found by observation. This we found by observation. Okay, can there be more than one common value? Okay, is it clear up to this point how we found? What are we doing till now? Is it clear up to this step? Yes. Okay, so we found the multiplicative inverse of 2 mod 19 as 10. So this line, this step simplifies to this one. 9 into each of them is now 10 basically. So 9 into, because it is the multiplicative inverse of 2 mod 19. So 9 into 10 into 10 into 10 into 10 into 10. That is 9 into 10 raised to 5 mod 90. Okay. Now this is what we want to find. This is the answer for 9 into 2 raised to minus 5 mod 90. Now how can I find that? For that, I split 9 into 10 raised to 5 into something for which we can directly calculate mod 90. That is the remainder. We can directly calculate. So I broke this down into 90 into 100 into 100. You can also break it down into, let's say, 900 into 1000. You can also break it down into 900 into 1000 mod 19. It is up to you. Yeah, 9 into 1000 into 100. That would also be fine. Okay. So whatever. So I broke it into 90 into 100 into 100 mod 19. If you break it as 9 into 1000 into 100, you will have to find the remainder for each of them. So for this one, for 9, it is 9 only. I'm explaining your case. So for 1000, you'll have to find it, and for 100, you'll have to find it. What I did, I'll explain here. So for 90, if I divide it by 19, 90 divided by 19, the remainder is 14, 1 4, because the closest factor is 7, closest multiple is 76. Okay, 19 fours are 76. Okay, so this gives us 14. For 100, the closest multiple is 95. 19 fives are 95. So remainder is 5. Remainder is 5. What we are doing? We are doing A into B into C mod M, let's say. Then it is like taking the individual mods and multiplying it. Okay, that is what we had studied in the properties of modulus. So we are calculating 90 mod 19, that is 14. 100 mod 19 is 5, and 100 mod 19 is 5. Okay, but still what we are getting is 14 into 25 mod 90. This is also not satisfactory. We want a remainder, basically. We want the non-negative residue. Yes. So we want the remainder, least non-negative residue. We want the remainder. So still we have 14 into 25 mod 19. Now for 25, again applying the same principle. Now when 14 divided by 19, remainder is 14 itself. When 25 divided by 19, remainder is 6. Okay, so that is how I got this step. All right. And then finally, I have multiplied 14 into 6, that is 84. Now 19 fours are 76. Uh, We want to find for 84. Remainder is therefore 8. This is our answer. Okay, fine. So this is, in fact, we are just at the second element of the list, and we actually found a match. We actually found a match already. We found a match at 2 raised to 3 and this one. Okay, that is, this was the thing now. Find a match between the two lists, g raised to I mod p and h g raised to minus nj mod p. Find a match. We found a match. Do you get this point? We found the match. Yes. Anyone has any questions? Okay, we found the match. 2 raised to 3 mod 19 is congruent to 9 2 raised to minus 5 mod 19. Okay, so I is 3. What is j? What is j? Yes, j is 1. Okay, j is 1. Now calculate your x. X is I plus nj. X is I plus nj, which is 8. Okay, so in fact, uh, where was our question? Yes. 2 raised to 8. You can verify this. 2 raised to 8 is 256. Divide 256 by 19 and verify whether you get the remainder as 9 or not. Okay, so 2 raised to 8 congruent to 9 mod 19. 256 divided by 19. Remainder is indeed 9. Okay, how is J1? So in the second list, we found h into g raised to minus n j. We found for j equal to 0, it was 9. And for j equal to 1, it was, okay, so j was 1. Verified. So this is this is how we solve using the baby steps and giant steps algorithm. This is how we can find the discrete logarithm. This is not a okay. So this is, what can I say? This is like testing the strength of the algorithm. Okay, this is not a part of your Diffie-Hellman key exchange. Okay, or as a matter of fact, even for RSS, sorry, RSA algorithm, even for RSA algorithm, the modulus is known to the public, as well as the when to use baby steps, giant steps method when, okay, when you have to solve this kind of a problem. Okay, you can see. Okay, can this problem be solved using any other technique? Had we seen, if you remember when we had covered the Okay, think about it later whether, but so when to use baby steps, giant step method, either the question will state that you have to find the discrete logarithm, or you can see this kind of a problem where you have to calculate the power for which here there is, we don't have one basically over here. Okay, or it's up to you. Like, okay, like this is the discrete logarithm situation. Either, okay, while designing the question, it will be clear in the question whether the method has to be specified in the question, so it will be clear. Okay, so what to do? Let's, okay, there is one more method. There is one more method to find the discrete logarithm. It's called as index calculus. Index calculus method. Okay, so let's say we want to find 2 raised to x is congruent to 55 mod 101. You know, this method is a little bit uh, okay. So just there is no set step of like no no fixed so what we have to do as the next step is you have to choose a small set of primes. Let's say we take three primes, three prime numbers, 3, 5, and 7. Take any three prime numbers, 3, 5, and 7. This set is called as a factor base. This set is called as a factor base. Okay. What we do now is we choose some random values. Okay. And we calculate 2 raised to r mod 101. 2 raised to r, where r are some random values. Okay. So we'll take any five random values. Let's say 2 raised to 7. Okay, we'll find 2 raised to 7 and 2 raised to 7 mod 101. So 2 raised to 7 is 128, mod 101 is 27. Okay, it is congruent to 27. Now you will try to express this in terms of the factor base. So it is congruent to 3 raised to 3, 5 raised to 0, 7 raised to 0, mod 101. Then take any other random value. Let's say 2 raised to 9, mod 101, which is 512. So remainder is 7. 512. 2 raised to 9 is 512. 101 fives are 505. Okay, so remainder is 7. So it is congruent to 7, which is congruent to 3 raised to 0, 5 raised to 0, 7 raised to 1, mod 101. Then let's take the next number as 2 raised to 17 mod 101, and it is difficult to calculate this without. So 2 raised to, we found for 2 raised to 9. Okay, for 2 raised to 8, it's a bit tough to go this way. Okay, so basically we'll do this for different powers of 2. Okay, okay. Now this will be okay. Okay, skip this method. Okay, because there are too many random factors involved. So let's skip this method. Let's just move ahead. Okay, because let's just focus on one method that you all have understood. That is the baby steps, giant steps method. Okay, index calculus. If you want, you can uh, study later. I will just, but it is quite a complicated way, complicated method. And why do we require this method? This is required only when P is large. That is, P is almost greater than equal to 20 digits. So I will share some article or video regarding to the index calculus, because this cannot be there in your tutorial or exam basically. And after watching the video and or going through the link, if you have any questions about that method, then I can solve your doubts individually about it. So let's just skip this method from the uh, curriculum point of view. Okay, I'll share the link later. This was about the discrete logarithms problem. Okay, in baby step, how to know if the algorithm is strong or weak. Is there any range? I No, I don't understand your question. Can you just unmute and ask the question?
Yes, sir. Sir, like you said that baby step and giant step is used to check the strength of algorithm. So here, like we got 8 as answer. So is there any particular range? Like how to know if algorithm is strong or weak?
No, okay, so from that, okay, so there is something called as space complexity and time complexity of an algorithm. Okay, so in the worst case, now we immediately found a match, but in so this algorithm takes. Okay, have you learned about the space complexity and time complexity of algorithms?
Yes, sir. But like basics.
Okay, so uh, this algorithm actually involves calculating g raised to I mod p n minus 1 times, and calculating h into g raised to minus nj mod p n minus 1 times. So this effectively takes exponential time. This takes exponential time, and one of the list we definitely have to generate. Okay, now you can have some tweaks in this algorithm, like you'll generate one value of this list, one value of that list. But here we instantly found a match at j equal to 1. But in worst case, we'll have to go up to n minus 1. Okay. For if that happens, then the complexity is exponential in time, and exponential means that there is polynomial time and there is exponential time. Okay. So uh, if there are in general, so polynomial time means it is a polynomial in n. That is, yeah, polynomial time, exponential time is n raised to n. Like, not only n raised to n, it can be, let's say, any a raised to n, some base raised to n. N is in the exponent, and polynomial is, yeah, o n raised to x. That is o of n, o of n square, o of n cube. These are all polynomial times, and o of 2 raised to n, o of 3 raised to n. Okay, in general, o of a raised to n. These are exponential times. So it takes. So what is even worse actually is the earlier brute force method. Brute force is the worst. Okay, brute force is the worst. Followed by that, this actually, if we calculate in parallel, like, you know, so we could have uh, so here n was 5, so 2 raised to 4. But let's say that I equal to 3 and j equal to 1 was a match. So if we were calculating it in parallel, like, I equal to 0, j equal to 0, I equal to 1, j equal to 1, I equal to 2, j equal to 2. If we calculate in that way, we need not even generate the entire list as such. Okay. So in that case, it saves some time compared to brute force. Okay, but it requires more memory. Space complexity is more compared to brute force because we need to store the values to compare them somewhere. Little more space complexity. And how do we know? Because it takes exponential time to crack this. That's why. Okay. And the actual integers that you have, the prime numbers, like we saw in this index calculus method, there not only 20, there are sometimes up to 100 digits of prime numbers or even more. So although this procedure is good for 2, 5, 7, 19, 17, 23, for such large prime numbers it becomes difficult. Okay. So the next thing to discuss is uh, first is the uh, fractalization. And okay, so in the next lecture we'll see about primality testing, because there are only 5 minutes left right now in this lecture. Okay, I'll just show you uh, one thing. Let's say we want to factorize a number. Okay, there is something called as the fundamental theorem of arithmetic. Fundamental theorem of arithmetic, which says that we can, either a number will be a prime or it can be expressed as a product of primes. Either a number will be a prime or it can be expressed as a product of primes. Okay, a number is either a prime or a product of primes. That is the fundamental theorem of arithmetic. Now let's say we are given any random number. Okay, and we want to test whether that number is a prime number or not. And it is not possible to decide that just by looking at the number. Let's say n is equal to 401. So how will you find whether 401 is prime or not? Okay, so that is what we'll try to do in the next lecture. But the brute force method is obviously you try from the smallest prime, you try with 2, no. So you have divisibility test. It is not an even number, so not 2. 3, the sum of the digits is not a multiple of 3. 5 does not end in 0 or 5. 7, is there any test for 7 that you know of? If you know it, it's okay. Then otherwise you can just directly, you know, 7 fives are 7s are, and it does not. Uh, then try with the next prime, which is 11, not divisible. 13, not divisible. 17, not divisible. 19, not divisible. 23, again not divisible. So okay, there is a proposition that, okay, we'll see it in the next lecture, but there is a proposition that, if n is 401, you need not go beyond square root of n to check for that. Okay, so square root of 401 is approximately 20. So you need not go beyond 20 to check, basically. So because none of the primes within 20, less than 20, is a factor of 401, therefore 401, therefore 401 is a prime number. Got this? Okay. Any questions? Any doubts? Any questions? Okay. Okay, then I'll end the lecture. Thank you. Okay. A question: if n is a bigger value, yeah, that we'll see in the next lecture. Will you repeat this in the next lecture? Yes. Okay. Thank you.